Alright, this is the first main lecture video of the third week. In this video, let me talk about the duality. So in the previous week, we talked about the two major problems about consumption behavior, utility max and expenditure mean. And from the UMP, we derived Walrasian demand. And Walrasian demand is the optimal demand schedule when the consumer attempts to maximize his own utility, given price factor P and consumer's wealth W. So Walrasian demand becomes a function of these two parameters. And substituting this Walrasian demand into the original utility function, we obtain the value function, the indirect utility. And indirect utility is denoted by function V. That tells us what is the highest level of utility attainable given price factor P and consumer's income W. So just like the Walrasian demand, indirect utility depends on these two parameters. And we also examine its counterpart EMP. And from that, we derive the Hicksian demand. And Hicksian demand can be thought of as another optimal demand schedule, but now consumer wants to minimize expenditure. So from that, we can infer consumers' behavior in the market, but now the objective is to minimize expenditure, but he wants to achieve certain level of utility. So Hicksian demand becomes a function of these two. And substituting this Hicksian demand into the expression of expenditure, we obtain the expenditure function. So this function tells us what is the minimum expenditure necessary for attaining certain level of utility given price factor P. So Hicksian demand and expenditure function depend on these two parameters. Good. So when we tackled on these two problems in the previous week, we adopted the Lagrange multiplier method. And remember the stationary condition in the method that gives us the necessary condition for an interior solution. And the condition in the UMP requires that gradient vector U at the optimal solution is equal to, so I didn't specify the Lagrange multiplier here, but gradient vector is equal to lambda times P. And then the condition for the EMP, expenditure mean, we almost have the same condition. So we have almost the same condition, but the only difference is the Lagrange multiplier now appears on the left-hand side. So at least for geometry interpretation, these two conditions have the same meaning. So no matter whether the consumer wants to maximize utility or minimize expenditure, the optimal bundle is determined by the condition that gradient vector and price vector should point to the same direction. So the same condition suggests that the two problems are closely interrelated. So this is the so-called duality coming from the convex optimization theory. We are not going into the details about duality because that is beyond our course. But if you are currently taking math econ class, you're gonna study that more about that duality at the end of the course. So instead of going into the duality, we pay attention to the relationship between these two specific problems. But essentially, duality says every convex optimization problem can be put as the dual problem. And then dual problem and the original problem have this very close relationship. All right, so as a matter of fact, we can see that due to duality between these two, we have a very close relationship between these four components. Okay. So in this video, we look into the relationship between these two value functions and these two demand functions. Okay, one by one. All right. And as a consequence of this duality, we can derive the most important result in consumer theory, that is the celebrated Slutsky equation. All right, so let me begin with the relationship between the two value functions, indirect utility and expenditure functions. So the relationship is described in this theorem 1.9, and we suppose that preference relation satisfies the three basic assumptions. So completeness, transitivity, and continuity. Okay? And plus, we are going to assume monotonicity. And by the representation theorem, we know that under these conditions, there exists a nice utility function u continuously increasing and representing the consumer's preferences. Okay. All right, and then we need one more condition, that is a strictly positive price vector. Okay. And under this positive price vector, we have the followings. Let me mention about the law of this condition a little bit. Remember, if some commodities are freely traded in the market, okay, freely traded in the market, then if we think about the budget set that expands without any bounds, okay, that is no longer triangle in the commodity space. Yeah, so that means it's no longer compact. So although we have a nice utility function, continuous, we may not have solution to the UMP or EMP. Okay, because when we make sure the existence of a solution, we apply the extreme value theorem. And extreme value theorem stems from the two conditions. Objective function is continuous, and choice set is compact. Okay, but if price vector is not strictly positive, then choice set is no longer compact. So one of the conditions necessary for extreme value theorem breaks down. Okay, so in that case, we no longer guarantee the existence of a solution, meaning that we don't know whether Walrasian demand exists, and we don't know whether Hicksian demand exists. Okay, so because we don't know the existence of a solution, we don't know what the indirect utility function looks like and expenditure function looks like. Okay, so we can't obtain this result. So the positive price vector is essential for existence of every component. Okay, good. So positive price vector means we only deal with goods having some economic value. So we exclude all neutral goods and bads. Okay. All right, and then the first relation tells us so originally expenditure function depends on price vector P and U. Okay? But in place of U, if we substitute indirect utility, we obtain this consumer's wealth. So everything is cancelled and we are left with just W. Yeah? Just like the inverse function relationship. Remember, if we have two functions f and g, and we combine them using composition, okay? And if the function g is the inverse of f, then these are cancelled. Okay? So we have just the inner argument x on the right hand side. So in this, in the similar vein to this, we can say from this relation, indirect utility becomes the inverse function of E with respect to U. So with respect to the second argument. Okay? So everything is cancelled and we are just left with the consumer's wealth. Okay? And then interchanging the law of these two functions, if we start from the indirect utility, that originally depends on P and W. Okay? but instead of W, we substitute expenditure function. Then everything is cancelled, and we are left with just the consumer's target utility. So the second relation tells us expenditure function can be seen as the inverse of function v with respect to W. Okay? And so one more implication from this theorem is that, suppose that we are given information about the expenditure function. Okay, we know what this function looks like. Okay? And from this relation, we can recover the indirect utility, because indirect utility is given by the inverse function of E. Okay, so setting this expenditure function equal to W and then solving for U gives us the information about indirect utility. Okay, let me give you a specific example. So suppose that function E looks like this. Say U plus 2 times P1 plus P2. We know expenditure function is increasing in every argument, because if the consumer anticipates inflation, minimum expenditure is increasing, and if the consumer wants to achieve wants to pursue a better living standard, so this target utility gets higher, then minimum expenditure is also increasing. Okay? This is why every coefficient of each variable here is given by strictly positive constant. Okay? And the way to recover indirect utility from this, we set this expenditure function equal to W. Okay? And then solving for U, we obtain this. Okay? And then this becomes the indirect utility. We have P comma W. Alright, and then making use of the second relation, we can recover expenditure function from the indirect utility. So if we know what indirect utility looks like, for example, function v is given by, say, W over P1 plus P2. Okay, remember, function v is increasing in W but decreasing in price. Right? If the consumer gets wealthier, the highest level of utility, consumer's well-being, is increasing. Yeah? But in case of inflation, consumer's well-being, it gets worse and worse. So this is why I put the W on the top and price factor on the bottom. Okay? So there's a negative association between price factor and the consumer's well-being. Okay? And then the way to recover expenditure function is set this equal to U. Okay? And solving for W this time gives me U times P1 plus P2. Okay? And this expression is the expenditure function, E of P comma U. Alright, and then now we are going to prove this this result. The proof is really simple, intuitive, and not difficult to understand. Okay. Alright, so let me first prove this first result. Yeah? So think about the relationship between this expenditure function and W. Okay, and to help you understand, to help you follow the proof, let me rewrite this as P comma U equals W, and U is given by this indirect utility. Alright, so this is what we want to show, and U is given by this. Okay? And the first observation, so by comparing these two, we can first observe that the quantity on the left hand side, the expenditure function, must give us a lower number than W. So we have this inequality. Yeah? Why? Because we know that U is this indirect utility. Okay? So if we interpret this, if the consumer has some money W in hand and he faces this price factor P, then this U is attainable because indirect utility indicates that highest level of utility attainable. Okay? So if we know the value of this function V equals U, then this U is attainable at least. Okay? But the definition of E is the minimum expenditure necessary for attaining this level of utility. Okay? So with this money, we know that this target utility is attainable. So what is a minimum expenditure for attaining this level of utility? That should be lower than, at least lower than this W. Yeah, so we have this inequality. But this is a weak inequality. We can't say this is a strictly lower than this. Right? So this is what we want to show. Right? And we obtain this inequality. Right? So in order to get the desired result, the only thing we have to show is that the strict inequality never happens. Never holds. Right? So now the way to prove this, the way to prove that strict inequality never holds, that is done by proof by contradiction. So suppose to the contrary that this strict inequality holds. Okay? Now we are going to derive some contradiction. That means because expenditure function is increasing in U, okay? If this quantity is strictly lower than W, if we increase the target utility U slightly, okay, say from U to U prime, okay, then we're gonna get the same value as W. Okay? So we increase U prime to the extent that this function E gives us the same value as W. Okay, so here U prime is higher than U. Okay, then comparing these two equations, these two information, then we can see our immediate contradiction. You know, this U, by definition of V, is the highest level of utility attainable with this money. Okay, but this equation tells us, you know, with the same money, the consumer can achieve even higher level of utility. Yeah, that is a minimum expenditure necessary for attaining this higher level of utility than U. That turns out to be W, meaning that with the same amount of money, the consumer can achieve a higher level of utility than this indirect utility. That is a contradiction. Yeah? So we must have equality between these two. Alright, so that proves the first result. And to prove the second result, you know, the proof is almost the same. So we want to show that V of P comma W equals U. But by the way, W is given by this expenditure function. Alright, and then so you know, we can start with this inequality. Now function V is at least higher than U. Okay, because the way to see this is, you know, by definition of E, we know that with this money, the consumer can achieve this level of utility. Okay, but V indicates the highest level of utility with the same amount of money. Okay, that should be higher than, that should be at least higher than this U. Okay, so we have this inequality, but we want to show equality. Okay, so the only thing we have to do is this strict inequality never happens. Okay? And the proof goes the same way, or we use the proof by contradiction. So suppose to the contrary, this inequality holds. Okay? but now V function is increasing in W. So we now reduce the wealth, the amount of wealth, to the extent that this function gives us the same value as U. Okay, here W prime is lower than W because function V is increasing in W. So if this guy is higher than U, then we can reduce the size of this W to the extent that these two are equal to each other. Okay, now comparing these two, we can see some contradiction. So remember, W is a minimal expenditure. The consumer has at least this amount of money to achieve this amount or this level of utility. Okay, but this equation tells us with a smaller money, the highest level of utility attainable is equal to U, meaning that consumer can achieve the same level of utility with a smaller money. That is a contradiction. Okay? So we have these two results. So indirect utility can be seen as the inverse function of E and vice versa. Expenditure function can be seen as the inverse function of V. Okay? So the two value functions have the inverse relationship. Okay? And in the next slide, we compare the two demand functions. So now we establish the relationship between the Walrasian or Marshallian demand and Hicksian demand. Okay? So we are going to make assumption. So we are going to make the same assumptions about the preference relations, and we have the strictly positive price factor. Okay? And it turns out that Walrasian demand is equal to Hicksian demand. Okay? But now we substitute indirect utility in place of the target utility on the right hand side. Okay? Then these two demand functions indicate the same demand schedule. Okay? And then vice versa. If we substitute the expenditure function in place of W in the Walrasian demand, okay, then we obtain the Hicksian demand. Okay, so that describes the relationship between the two demand functions. So from Hicksian demand and indirect utility, we can recover Walrasian demand. Okay, and then with Walrasian demand and the information of expenditure function, we can see what Hicksian demand looks like. Right, so so in this lecture video, let me present the intuitive proof for this result only, and the proof for the second result is exactly the same. Okay, it's based on exactly the same idea. Okay, so to prove that, we are going to work with the two commodity, only just two commodities. Okay, suppose that there are just two goods. Okay, and we formulated a UMP and solved it out. Okay? And to find out the Walrasian demand for each commodity. Okay? So the Walrasian demand for good 1 and Walrasian demand for good 2. Okay? And then we substitute into the utility function and obtain the indirect utility. Okay? So the way to solve this in case of two commodities, we can make use the tangents condition. Okay, remember, at the optimal choice, margin line is tangent to the indifference curve. Okay, in other words, MRS equals P1 over P2. Okay, extending to L commodity space, this is going to be gradient of U equals lambda times P. Alright, so we know that at the optimal choice, some indifference curve will be tangent to the given margin line. Yeah? That is how we determine the Walrasian demand in the UMP in case of two commodities. Okay, so the level curve, so the level of this indifference curve indicates the indirect utility. Yeah, so that is the highest level of utility obtainable given this price vector P and W. Okay. In other words, if we think about this indifference set, it can be written as the set of bundles such that U of X is equal to indirect utility. Alright, so given this information, now we consider the following expenditure minimization problem. Okay, so now we set the expenditure given the same price vectors, now given this constraint. But instead of target utility U, we plug in this indirect utility. Okay? And then the way to solve this EMP, okay? So now we pin down this indifference curve. Okay? This is the highest level of utility, right? And then we adjust the height of this line segment with the same slope, because the slope of this line segment is determined by the price vector. Okay? And the height of this is given by the expenditure. Okay? So we wanna figure out the level of this expenditure. In other words, the height. Okay? So starting from the origin, we start to increase the expenditure. Okay? Increase the height of this line segment. Okay? Up to the point that up to the point where this budget line is tangent to this indifference curve. Okay, and then very intuitively, not surprisingly, we are gonna have the same point. So at the same point as before, this line segment will be tangent to the indifference curve. Meaning that the solution to this problem, EMP, so that can be written as Hicksian demand given price vector P and given this indirect utility. It will be the same as the previous Walrasian demand. Okay. So solution to this problem has to be the previous Walrasian demand. So by the same line of reasoning, you can show that these two are equal to each other. Okay, so now we have the complete link between the four components in the UMP and EMP. So suppose that we have a function V. So we know what the indirect utility function looks like. Okay? And by the previous proposition, we can recover expenditure function. Right? And then, from expenditure function, we can recover Hicksian demand. Because by Sheffard's lemma, we know that Hicksian demand is simply the derivative of this expenditure function. So if we wonder Hicksian demand for good K, what we can do, we can just simply take the derivative of this E with respect to P sub K, the price of good K. And we can obtain Hicksian demand. So if we know expenditure function, we know every Hicksian demand for the Hicksian demand for every good. Okay? And from that, we can recover Walrasian demand. Okay? So by substituting this indirect utility into the place of U. Okay? So that gives us this X star. Okay? And then the link between these two is straightforward, because indirect utility is the value function of UMP. So if we know X star and if we know utility function, then we can recover. So we can figure out what the indirect utility looks like. Okay, and we may start from here, expenditure function. Okay, and we know then Hicksian demand and Walrasian demand and indirect utility. Okay, and we can go back to the expenditure function by the previous proposition. All right, and so the link between these two is a slightly weak because as I told you, the way to find the indirect utility from the Walrasian demand, we need information about the utility function, right? So and furthermore, so from this, the way to figure out the Walrasian demand, we have to take 3 steps. 1, 2, 3. Yeah? That is sometimes a little bit cumbersome. And the next result coming from the duality, the so-called Roy's identity gives us leeway. Yeah? So we don't have to take these 3 steps. Yeah? Just by taking 1 step, we can find out the Walrasian demand from the indirect utility. Yeah? That is given by this slide. So under the same conditions and plus under the technical condition that function v is a differentiable. Yeah, so we have a nice, very smooth function indirect utility. Yeah, and the way to recover Walrasian demand is this. Yeah, so we have to take the derivative of function v with respect to p sub k if we wonder demand for a good k. Okay? And we have to take the derivative one more time now with respect to w. Okay? Then we can obtain the we can find out the Walrasian demand for a good k. Yeah. The way to derive this formula is really simple. Okay, so we have this identity. We know expenditure function is the inverse function of v. Okay, so if we substitute expenditure into the place of w of indirect utility, we obtain the target utility. Okay, so given this identity, we take the derivative with respect to p sub k. Okay, when we wonder Walrasian demand for good k. Okay, then u is a constant. Okay, so after differentiation, left hand side becomes 0, and the right hand side, because p sub k appears in 2 different places, here and here. Okay, so we should consider the total derivative. Yeah? So we first take the derivative with respect to p sub k. And remember, this can be written as v of p comma w, and w is e of p comma u, and p sub k appears here. Okay, so using the chain rule, we first take the derivative with respect to w, okay, and then multiply by the derivative of this with respect to p sub k. So p sub k, but this guy can be written as derivative of e with respect to p sub k, because w is given by this function e. Okay? And by Shepard lemma, we know that this is a Hicksian demand for good k, p comma u. All right, but u is given by indirect utility. Okay, so we can plug in this indirect utility here to obtain h sub k, p comma v of p comma w. Then by the duality between Hicksian demand and Walrasian demand, we know that this is simply Walrasian demand for good k. Okay, so by this for this reason, the derivative of the right hand side becomes this times x sub k star. Okay, so we take this portion and the 0 on the left hand side. Okay, so now we can solve for x sub k, moving this term to the left hand side, and dividing both sides by this derivative, we obtain this formula. Alright, cool. So if we think about this negative sign, the reason of this negative sign, because the sign of this derivative is positive, because indirect utility is increasing in W. So the derivative must have this positive sign. But the sign of the top is a negative. Indirect utility is a decreasing function in the price. Yeah? This is why we needed to have one more negative sign in front. Yeah, for the expression of Walrasian demand. Alright, so in this video we examine the the relationship between the two demand functions and the relationship between two value functions, the so-called duality. There is one more important application of this duality, the classification, and that is what we are going to study in the next video.